Hello, in this tutorial I will explain how to use SDRAM, build on dual clock FIFO and deal with signals in multiple clock domains. Our goal is to build a system which will write an image data into SDRAM, translate into dual clock FIFO and eventually display it on a FPGA monitor. Here is a quick overview of our project. It consists of external SDRAM, SDRAM controller, dual clock FIFO, FPGA component, and the main FPGA architecture. Notice we have two clock domains, 143 and 49.5 MHz. The actual FPGA design and SDRAM are clocked at 143 MHz. The FPGA component works at 49.5, which corresponds to the pixel clock. The SDRAM chip can deliver data via refresh and pre-charge period, so we will need to buffer the data for the FPGA component. Because we are moving data between different clock domains, we are using FIFO with dual clock, writing at 143 and reading at 49.5 MHz. Crossing clock domains has some deadly pitfalls one must consider, but don't worry, I will explain you how to deal with them. Let's begin. First, import the pin assignments. For this tutorial I wrote a simple FPGA component which takes care of the FPGA interface and delivers some additional signals. I presume you already know how the FPGA interface works, so I will skip the detailed explanation. If you are not familiar with it, check my other tutorial about this topic. Alright, now let's build the QSys system with Altera SDRAM controller and PLL. The SDRAM controller will take care of all critical and complicated SDRAM timing. The PLL will generate all necessary clock signals. The communication between the SDRAM controller and our VHDL design will happen through the Avalon memory mapped slave interface. Go to Memory Interfaces and Controllers and choose SDRAM controller. Now configure your SDRAM chip according to your development board. The settings and timings are valid for DE1-SoC board from NIOSII. For more information, read the datasheet for your particular SDRAM chip. Next, add the PLL. Set the reference clock. In my case, it is 50 MHz. For this project, we will need 4 clocks, 143 MHz for SDRAM chip, SDRAM controller and the main process, 49.5 MHz for the FPGA component. Since the SDRAM chip is physically separated from the FPGA, we need to shift its clock by about -50 degrees. This will make sure the data on FPGA is valid and stable on the rising edge of SDRAM clock. Connect the 143 MHz clock to SDRAM controller and extract the rest clock signals. Also extract Avalon interface and controller conduit. The conduit will be connected directly to the SDRAM. The communication with the chip, such as read or write operations, is done through the Avalon memory mapped slave interface. Now let's write the VGDL code. Add all necessary FPGA connections, such as clocks, interface pins, and so on. Now go back to QSys and copy the component declaration. Add this component into your architecture. Map the board according to the required signals pins. You will also need additional signals for the Avalon interface. I will explain how the Avalon interface functions in a minute. The Avalon interface consists of following signals. Chip select, enable the SDRAM chip. Byte enable, choose if you are addressing lower or upper byte of the memory. Write, read data. Ports for reading or writing data from or to SDRAM. Wait request. If SDRAM is busy with precharge or refresh or for any other reason can be accessed, the signal is set high, else it's low. Read data valid. Is set high if requested data is ready, else it's low. Read enable, write enable, and address are self-evident, I think. Next, let's add the VGA component. It's a simple VGA controller with some additional useful output signals, such as begin of new frame, end of current frame, and active video flag. The active video flag is set high if the current pixel doesn't belong to any blanking interval. You can find all project files on my GitHub. Okay, for the dual clock FIFO, we need two dual clock RAM. Create new HDL file and click on Insert Template icon. Now you can set the RAM size and data width. The FIFO has two ports. One port is clocked with 143 MHz and serves as input. This port will accept data from SDRAM. The second port is clocked at 49.5 MHz and is connected to VGA component. It will deliver the buffer data on demand. Eventually, let's assign the shifted 143 MHz clock to the SDRAM clock input and also take care of some constant signals like reset, byte enable, and so on. Before we go on with this project, let's take a closer look at Avalon interface. The write waveform is pretty simple. You set the write enable signal low, and while the write request is not assigned, you can write data on each rising edge of the clock. The reading operation is a bit complicated. This SDRAM controller can store up to 7 read requests. As soon as data is available, the read data valid signal goes high and the data is outputted in the requested order. That means, while a write request is not set, you can put some data request in a queue. Once the queue is full, the write request goes high. Because the SDRAM needs a few clock cycles after read enable is set before it outputs requested data, it is strongly recommended to read big packets of data in one read session, instead of switching read enable on and off all the time. You will see what I mean a bit later. Alright, let's talk about FIFO. The FIFO is a circular RAM with read and write addresses. Where the RAM is filled at fast 143 MHz, the read process is relatively slow at 49.5 MHz. Now, let's see when the FIFO is full or empty. The FIFO is empty if the read address meets the write address. In other words, the read address made the whole circle and reached write address from behind. In this case, no new data is available and FIFO is empty. The full condition is met if the next address we are going to write to is equal to read address. Since we don't want to overwrite valid data, we stop here. In our design, we will also need an additional full pointer, because we read data from SDRAM not at the same clock cycle as we requested. That's why we must take care to request as much data as we can store in a free FIFO space. With the full pointer, we are allocating FIFO memory for new data. As soon as it reaches read address, the FIFO is full. It is also important to set a constant distance between write address and full pointer. This constant distance will prevent the overwriting valid data due to some delay in our design. Next, if read data valid signal is high, we copy data from SDRAM into FIFO and move the write address. Another thing we should talk about is the clock domain crossing. If we transfer a signal from one clock domain into another, some critical issues can happen. Let's see what happens if the transferred signal from 143 MHz domain is changing its value right at the rising edge of a receiving flip-flop in 49.5 MHz domain. The receiving flip-flop doesn't see a proper logic level, but something in between. As a result, it falls into metastable state. Its output oscillates between 1 and 0. Eventually, it settles down to some random value. This oscillation will cause all imaginable and unimaginable problems to your design. For example, one part of your FPGA can interpret the output signal as 0, the other as 1, or even the whole FPGA can fall into an uncontrollable state. But don't worry, there is a simple solution. Before we can use a signal from another clock domain, we should synchronize it to additional flip-flop. This way, if the first flip-flop falls into metastable state, it will most certainly stabilize at the next clock cycle, and the second flip-flop will register a valid logic state. After this synchronization, the signal can be used without any problems. All processes will always see the same value. The only one case you should always take in account is that the synchronized signal can stabilize at wrong value. For single-bit signals it's not a big deal. Let's assume a 4-bit counter is changing its value from 15 to 0. At one clock cycle, all 4 bits are changing its state. If some of these bits are registered at old state and some at new, all possible intermediate values can appear at the output. They are stable but wrong. As we can see, a dual flop synchronizer is not enough for multi-bit signals. In this project, we want to send the write address from 143 MHz domain to 49.5 MHz domain to detect the empty condition. If an arrived address is not correct, the empty condition will not be detected. In fact, the addresses are nothing more than a simple counter, which increases only by 1 at a time. Luckily enough, there is a clever solution for cases where the signal of interest is a counter. The solution is gray code. The gray code is a binary numeral system where two successive values differ in only one bit. For example, from 7 to 8, the binary code changes all 4 bits, while gray code only 1. Since only 1 bit is changing, after dual flip-flop synchronization, the arrived data could only be an old or a new one. Any intermediate data are possible. Even though there is a possibility to miss a new address, it's not a big deal if you can sample the address multiple times before it changes. Now you have an idea how to cross clock domains correctly. Let's go on with the project. Let's take a look at 143 MHz domain. At the beginning, you see the dual clock synchronization for next frame signal of the VGA controller. You can also see the dual flop synchronization for address 2, which is read address of FIFO. The data arrives in gray encoding, and after synchronization, it is converted back to binary. Before sending address 1 to 49.5 MHz domain, we encode it to gray code with binary to gray function. The main process consists of two states, writing and reading from SDRAM. Writing to SDRAM is simple. While wait request is not set, we assign new address and data each clock. As soon as SDRAM address reaches certain value, the writing process is ready and we can pass saved data to the VGA component. The FIFO buffer has two states, wait and active. Initially, the buffer is empty and the wait state is 0. In this state, we request new data from SDRAM while wait request is 0. Meanwhile, we also move the full pointer. If the full pointer is equal to read address, we stop requesting new data since there is no free space remaining. Once the buffer is declared full, it goes into wait state, sets the restart pointer and the VGA flag. The VGA flag tells the VGA process that the buffer is filled and ready. If read data valid is 1, write new data into FIFO using write address. The restart pointer reactivates the reading process once there is enough free space available. Remember, SDRAM performs much better if you read big packets of data instead of reading single address per reading session. In my case, one reading session reads 64 bytes. If the VGA controller sends next frame flag, the reading process ends and new data is written into SDRAM. This is the VGA process, clocked at 49.5 MHz. As you can see, there is also some gray code conversion and dual flip-flop synchronization. If buffer is ready and start of new frame is detected, start outputting image data. Also check if the buffer is not empty. Here is a quick look at binary to gray and gray to binary conversion functions. Again, you can find all files on my GitHub. By the way, if you like this video, give it a thumb up. Just for the testing purposes, let's write a black circle to SDRAM, read it from there and show it on the VGA monitor.